So section 4.3 is non-standard states. So standard states are here, these conditions, and if these are not met, then it's a non-standard state. And one thing that we've really not mentioned since we talked about it this day is Q. And it came up yesterday in the questions. Well, it came up in an answer that I showed you, where they phrased their answer in terms of Q and K, and nobody else did. And so this is one thing where AP really likes it if you can phrase answers in terms of equilibrium. So we'll talk more about that and that question specifically at some point. So in section 4.3, there's quite a bit of writing here. I'll tell you what, I'll just print this sheet for you. So you don't have to write it all down, you can just listen. So, sign of free energy. So idea number 3, a reaction will proceed to minimize its free energy. So minimize free energy. And of course, that's delta G. This number wants to be as small as possible, which is kind of what we go with because we want the sign to be negative. And so the lower it goes, the better it is. And so there's a table here. It says when the free energy is, when delta G is less than 0, it's decreasing. Sort of like that. When delta G is greater than 0, it's increasing. Nothing really new here. And when it's equal to 0, it's not changing, which means there's no change in free energy. It's probably not even a reaction happening. And in terms of the reaction, that means that this one is thermodynamically favorable. When delta G is positive, it's unfavorable. And when delta G equals 0, we are at equilibrium. So what happens to the reaction? How will the reaction proceed? When delta G is negative, it's a thermodynamically favorable reaction. It's going to happen as written, or what you might call in the forward direction. It's going to go reactants to products like we would expect. If it's thermodynamically unfavorable, meaning delta G is positive, it's not going to happen in the forward reaction, but if you turned it around, it would work. And so the reverse reaction happens. And if we're at equilibrium, it's really not going to proceed in the direction. Here is where we relate it to Q versus K. What does it mean? And a quick review on Q and K. I like to put them on a number line and not really assign them actual numbers, but let's say that this is K. This is where we're at equilibrium. This is the equilibrium constant. What happens if Q is less than K? Well, Q on the number line is always trying to get to where K is. And if you follow this arrow, it's proceeding in the forward direction, which means that Q is less than K. if you were to put Q over here where Q is greater than K, draw the arrow, it's going in the reverse reaction. And how are they related when we have equilibrium? They are the same. Q equals K, that means our reaction is at equilibrium. And so there's a formula that you have, and it's already written on here. There's a relationship between delta G and Q. So the delta G of the reaction equals the standard delta G of the reaction plus R times T times the natural log of Q. This is not the exact form that you see on the AP formula sheet, but there is a similar one. As it says, this is the gas constant using joules and moles in Kelvin, and temperature has to be in Kelvin. I probably won't do all of these in example 1, but I'll do a few of them. Consider the reaction N2O4 gas and NO2 gas. Okay. I don't know how much life this board has left in it. So the standard delta G is positive 6, and K equals 0.09. There. So these are some givens. And trial number 1, we're given a partial pressure of each of these, but nothing else. So partial pressure of N2O4, partial pressure of NO2. Then it wants to know Q. So in order to find Q, we have to have the equilibrium expression. For this reaction, the equilibrium expression is not right exactly. Pressure of NO2, and this one's squared because the coefficient over pressure of N2O4. And so we're going to plug our numbers into this and just verify that I wrote this down right. What'd you get? Pretty close to 0? Yeah. Okay. So it says round to the nearest hundredths place, and so Q here is 0.00. And comparing Q and K. Q is 0.00, K is 0.09, Q is less than K. If I drew my number line, here's Q, here's K. Q is always trying to get to where K is. This is going to go in the forward direction. I skipped one. We'll come back to this delta G. Direction forward. And the delta G here, we're going to use our formula that we just found. delta G for the reaction equals the standard delta G for the reaction plus RT times the ln of Q. And so we have some numbers. This one's positive 6. R, we're using 8.314 joules per Kelvin per mole. They gave us the Kelvin temperature, it was 298. And the ln natural log of 0.
But you can't take the natural log.
So let's see what this says here. I wonder if they put in the extra long number. Is you right about that? 6 plus. Yeah, that's a good point. I don't know how they got this negative 12.5. We'll put a question mark for this one because of this. All right. We'll leave that as a question mark. Like I said before the tape started, this doesn't come up but more than once on the AP exam. So. Let's look at, how about line 4? Partial pressures, 0.799, 0.403, and we need to find Q. Again, using that same equilibrium expression. What did you get, 0.2?
Yes.
0.20. And Q versus K. Q is greater than K. Delta G, we'll check that in a minute. And this one, the arrow pointing left tells me reverse reaction. Direction is reverse. The last piece is this delta G, and let's see if we can get the formula to work this time. Pause for a second. Projector decided to try something. That doesn't sound good. All right, well, I'm going to go ahead and calculate that while we see if the projector turns back on. And this might be our last question. 6 plus the gas constant, temperature is 298, and natural log of 0.2. Is it working? Oh, good. Okay, we're back. So, some things to consider. This over here is in kilojoules, and this is going to end up in joules. And so in order for our answer to make sense, put this in the calculator, we'll have to convert it. This comes out to be negative 39.87 joules per mole. And convert to kilojoules. Should come up with something approximately equal to positive 2 at 2.0. So you got?
Yeah.
Go back and check those numbers. They're not very good. So positive sign for delta G would also indicate thermodynamically unfavorable, but it would work in the reverse reaction. So we could go through all of these. I don't want to fill them in right now. Let's just stop it there, and I can finish up with the other class tomorrow.
Yeah.